Hello everybody, welcome back. As we start our next chapter, we're now on what chapter are we on? Like 16 or something? Look at that, we're just moving through this book. Chapter 16 is covalent bonding. What covalent mean? We already learned what valence was these free electrons. Covalence means basically sharing of those free electrons, those valent electrons. And that's what nonmetals like to do with one another. They both want an electron. Nonmetals have higher electronegativities, so they both want the electron. So rather than give it up, they find a way to share it. And that's what this chapter is about. So there is a little bit of biblical integration I can throw in for this chapter, which is hard to do sometimes in chemistry. But much like nonmetals have to live together in harmony, they have to share this electron, God wants us to do it as well. We should live together in unity. And it applies to nonmetal ionic compounds as well, because they have to find a way to get together. Well, atoms have to do the same thing. I like to say God created us as he created the universe for things to bind in unity, holding the universe together just as chemicals form bonds in specific ways as defined by the laws set forth by God, which we try to interpret or discover through science. So just wanted to, think about that. So quick review, valence electrons or valent electrons are the chemical properties of most atoms are determined by their valence electrons. Understand that, and those are the electrons in the outer s and p orbitals, the electrons that are the farthest away from the nucleus. We had the octet rule. Cations will lose an electron and anions will take an electron in order to get 8 valence electrons, which causes a lower energy state which they are happy at. In ionic bonds, one atom gives up an electron and another one gains an electron. They don't share it. And one of the reasons for that is because of the high electronegativity difference. And I might throw that in. I don't know if I put that into the videos for the last chapter, but if you have a high electronegativity difference, you form an ionic compound. If you have a low electronegativity difference, you form a covalent compound. I'm going to talk a little bit about something. Polarity is one of the topics of this chapter as well, which has to do with the differences in those electronegativity values. So let's start with what is a covalent bond. And I've drawn one here and on here. A covalent bond is one in which two atoms share an electron. That's what a covalent bond is. If one pair of electrons is shared, it's a single covalent bond. Guess what we call it if 2 pairs of electrons are shared? Double. If 3 pairs, triple. And the more electrons you share, the stronger the bond becomes. Sharing is caring. The more you share, the stronger you become. So here we have hydrogen, a single bond between 2 hydrogens because they each share 1 electron. But how do we know from a chemical formula we know how many atoms are involved? How do we know how many electrons are involved? Well, let's look at carbon. For instance, carbon has 4 valence electrons and 6 total electrons. 2 of the electrons are 1s2. So these are inner electrons. They're not valent. 4 of the electrons are valent. And carbon doesn't like to form ions, and one reason why you can think about that is because it's halfway between. Does it lose 4 electrons? Does it gain 4 electrons? And that's an awful lot of electrons to gain or lose, which would be destabilizing. So rather than form ionic compounds, carbon almost exclusively forms non-ionic compounds or molecules. And here, notice that carbon has 4 valence electrons, but it wants 8. It has 4, it wants 4 more. Hydrogen has 1 and it wants 2. So if a hydrogen shares 1 electron pair, it's happy. An electron pair is 2 electrons. Carbon needs to share 4 electron pairs. So it just needs to find stuff that it can share with. In the case of hydrogen, what happens is they're not giving up, they're not forming ions, but they're actually coming together. And the electrons are now shared between the 2 atoms. The hydrogen has them and the carbon has them. So now carbon has 1, 2, 3, 4, 5, 6, 7, 8, and every hydrogen has 2. Both elements have the electrons, both have an octet or duplex if you're hydrogen. Now you don't have to do it this way. You can just draw a line, and a line means 2 electrons are shared. So now carbon has 1, 2, 3, 4, 5, 6, 7, 8, and it's happy. I could also do carbon with oxygen. So here's carbon, and if you think, oxygen has 6. 1, 2, 3, 4, 5, 6. And if I put another oxygen over here, 1, 2, 3, 4, 5, 6. One way that helps when forming covalent bonds is just think, where can I draw lines? Well, there's 2 lines, and there's lines. Now carbon has 4 lines, which is 8 electrons. Oxygen has 2 lines, and then 4. These are paired electrons, and these are unpaired. But total, oxygen now has 8, and it would end up looking like this. And if I wanted to, I can also draw the unpaired electrons in there as well. So this is the electron dot structure of carbon dioxide. And you can also just as well, you can draw it this way as well. It doesn't matter which orientation it takes. So while CO2, the chemical formula tells me how many atoms, the structure can kind of tell me how those atoms are combined. Okay, and there are many here. So here's methane, CH4, ammonia, NH3, water, and it also gives an idea of why water is bent. Water is bent because it has those free electron paired, those unshared electrons, and those unshared electrons, and it actually makes kind of a tetrahedral. So if I was to draw it, I'll try and fill it up here. Here are these 2, and these are the kind of the hydrogen bonds. You can think of it like that. It's not going to form a flat square. Instead, it's going to have 2 of the, if you kind of twist your body and have 2 arms going one way and your feet going the other way, it forms what's called a tetrahedral. So that's a shape that looks like, I don't know if I can draw this well, but let's say this is coming out and this is going towards, and then these are in the same plane. And then here's your center item. Okay? Or I could draw it in many different ways. I don't know if I have a drawing here, but you can look online for tetrahedral and you'll see that's the shape it takes, because these things don't just form one shape. Like methane actually forms a tetrahedron. Water forms a tetrahedron, but 2 of the 4 are free unpaired electrons, and 2 are with the paired electrons with hydrogen. Where I'm getting at with this is there's something called VSEPR, which we'll get to later, but that stands for valence shell electron pair repulsion theory. And what that means is a molecule will form a shape in such a way that all of the free electrons, or sorry, unpaired electrons is a better way of saying it, and all of the paired electrons will be as far apart as possible. So the structure is most stable when those electrons are as far apart as possible, and a tetrahedron is the easiest way to have 4 points as far apart as possible. I'm going to come back to that. I just wanted to introduce it now. But the point is, all of these electrons are being shared in order to, or unshared, but you do it in a way that gives you 8 electrons when you're all done. So each carbon has 1, 2, 3, 4, 5, 6, 7, 8. Each oxygen has 1, 2, 3, 4, 5, 6, 7, 8, because each line counts as 2 electrons. And in this case, it's double covalent. In this case, they were all single covalent. You can also have triple, which is when you share 3 electrons. And the more electrons you share, the more stable you have. Now, I can't bring this YouTube video up within my YouTube video because that would break copyright rules. But go ahead and watch Simulation 16 at this website if you want to actually see how the electrons are kind of being shared. Now you can have, as I've already said, multiple types of covalent bonds. You can have 2 doubles. You can have, in hydrogen cyanide, you have a triple covalent and a single covalent. But if you look at those 3 structures up there, you'll see that every atom has 8 electrons around it. For instance, nitrogen has 6 shared electrons and 2 unshared electrons. Oxygen and carbon dioxide has 4 shared electrons and 4 unshared electrons. Or I could say two shared pairs and 2 unshared pairs. So sometimes you'll talk about them in terms of pairs instead of individuals. But each atom is trying to get to an octet, or duplex for hydrogen and helium. So those are covalent bonds. There is one other type of special covalent bond, I won't draw it, it's already on this, called a coordinate covalent bond. So these are regular covalent bonds. A coordinate covalent bond is a special type of covalent bond in which one atom will actually share both of the pairs of electrons. So carbon monoxide is a good example of this, and it's drawn, instead of with the line, you'll see that there's an arrow. That arrow means that the electrons are coming from oxygen to carbon. Okay? So if you look, the carbon has 4 pairs of electrons, or 8 electrons, and the oxygen has 4 pairs of electrons, or 8 electrons. So sometimes you can get to an octet by sharing unequally. The oxygen is being more giving than the carbon here, but they're both happy by the final arrangement, so it's okay. And that's called a coordinate covalent bond. Here's another example in ammonia when you form ammonium. So some polyatomic ions, in fact, coordinate covalent bonds are very common in polyatomic ions. Now, NH3, ammonia, is not an ion. And if you look at ammonia there, you'll see the NH3 there. If you add an H positive, which has no electrons, it's just a proton, you still have a situation where every element has an octet, but you have a net positive charge. So you can have coordinate and covalent bonds together. Coordinate covalent bonds, I guess the point I'm getting at is that they are very common within polyatomic ions. And basically a polyatomic ion is basically a molecule with a charge when you think about it. But it's acting like an ionic compound instead of a molecular compound because of that net charge. Because nitrogen is a nonmetal, hydrogen is a nonmetal, you end up with, you could have carbonate, sulfate, sulfur, and oxygen. They're both nonmetals. So when nonmetals come together to have a charge, they're a polyatomic ion. Ammonia being one of the few positively charged polyatomic ions, by the way. Usually they're negatively charged because nonmetals like to form anions, negative ions. So here's some of the polyatomic ions with their structures taken out of the book. You can see that many of them contain, not all of them, but many of them, like dinitrogen tetroxide. And these are actually not, the picture there is not polyatomic ions. The picture there is molecular compounds. But most compounds are polyatomic, and most polyatomic compounds contain both covalent and coordinate covalent bonds. And I need to change the title of this because it wasn't supposed to be polyatomic ions. It was just supposed to just be polyatomic. Where are we at? Yeah, that word ions was not supposed to be there. Wait, why is it still there? I just deleted it. There it goes. Okay. So most compounds are polyatomic, and most polyatomic compounds contain both covalent and coordinate covalent. They're both common, is what I'm trying to get at. Okay. And I'm going to stop there, and when I come back, I'm going to talk about the energy that's involved in these bonds. So you know that you can have single covalent, double covalent, or even triple covalent. That's really a matter of how many electrons are being shared. The electrons can be shared or they can be unshared. And I wrote paired here, and I should have said unshared. And these are shared because all of them are paired. So you have unshared and shared electrons. And when you do sharing electrons, that's called valent bonding.